That's the value of the angular momentum in the z direction. And L is j times j plus 1 square root times h bar. So I just used my L over there, took the square root. I have this nh bar, we just got from the LZ. So the angle theta then is the arc cosine then of m over square root of j times j plus 1. So I need to know the j's, I need to know the m's to find that out. Well, we can't quite do this yet. We need to do one more thing. We know the j's have values 0, 1, 2, 3, 4, 5. We know the m's have 0, plus or minus 1, and plus or minus 2, but we don't know the limits on them. All right, we have to establish those. So let's do one thing, and then we'll be ready to rock and roll with this. So there's what we've just done. So what about the values of x and y? Well, we can't know them, but maybe we can get some out of this. Again, from basic dynamics, L squared is Lx squared plus Ly squared plus Lz squared. Just like x squared plus y squared, z squared is r squared. Okay? We know L squared. We know Lz. We have those. So let's do this. I'm going to have Lx squared plus Ly squared is going to be equal to the total L squared minus Lz squared. Just separating the Lz from both sides. Take a note. These are a sum of two square values. So this is necessarily greater than 0. You gotta have it greater than 0. If you have an angular momentum value, you square it. It's going to be like negative x squared is x. It comes out there.
So with that assumption, with that assumption, assuming Lx and Ly are not 0 in any system?
It could be 0. I'll say, I'll go with you on that. That's exactly right. It could be greater than or equal to 0. So this is also greater than or equal to 0. Let's make operators out of those. In doing this, we know that the L squared operator minus the Lz squared operator on the wave function, okay? We have those answers. This is j plus 1, h bar squared, that's the L squared operating on the wave function, minus this squared, m squared, h bar squared. We had mh, or mh bar, so that case. This is greater than 0 or equal to, as Sarah points out exactly correctly. The only way that that can be true is for m has to be less than or equal to the absolute value of j. If it exceeds j, that turns into negative 0. Remember back in general chemistry, we gave you the rules on the quantum numbers. You had the principal quantum number, n, 1, 2, 3, but we're not there yet. But you had two other quantum numbers. You were given L and m sub L. L had values of 0, 1, 2, 3, and so forth. That was the s, p, e, and f orbitals. We're not there yet, that's atoms. But since it works the same way, you were also told that m sub L had values of minus L all the way to plus L in integer values. So if L was 2, m sub L could be minus 2, minus 1, 0, 1, and 2. That's where that came from, right here. So that's what this one then requires. So now we have our limits on m. We know that j can be 0, 1, 2, anything we want. So now we can figure out all the angles at which the molecule then rotates. So we have our relationships. Again, because this is a spherical rotating system, when we turn to a hydrogen atom, we'll have exactly the same results. We don't have to do it again. We're done. We just interpret it differently. All right? So anyway, So now we're ready to actually find some numbers. So I need to find out what angles an atom or a molecule is rotating. So I started off and I set J equal to 1 just as a given representation. So my angles, and of course MJ goes from 0, 1 to 2, so I did that in there. Sorry, I did it in kind of a cryptic way. But the MJ, if J is 1, MJ is -1, 0, and +1. So here's what we get. We have, for an angle, will be the arc cosine of -1 over, now J is 1, that's 1 times 1 plus 1 square root. So I just followed this exactly. Here's what I'm using. So I said, set n equal -1, J is 1, 1 times 1 plus 1. So we ended up being the arc cosine of -1 over the square root of 2. Well, that's one of them. If m is 0, remember m is -1, 0, or 1, the arc cosine of that is 0 over the square root of 2. Well, that's 90 degrees. So we'll put that. This one, -1 over the square root of 2 is 135 degrees. And finally, if I get the third one, then it is the arc cosine of +1 over the square root of 2. I get 45 degrees. So here's how this is interpreted. In a rotating molecule in a J=1 quantum state, it can rotate in 3 quantized angles. So here's how we start. You start the molecule flat because the angular momentum is vertical, it's what along the z-axis. So for the first one here, the arc cosine of +1 over the root of 2, I'm going to turn my thumb down 45 degrees. My fingers are curling in the direction which it rotates, so it's rotating like this. Okay? For the M0, I turn my thumb 90 degrees, so it is a vertical rotation. And finally, for the 135 degrees, I come all the way down, so there's that. So it can rotate this way, or this way. What about X and Y? We don't know. So when it rotates like this, then we have an entire cone at which it can be, this is still 45 degrees, but I'm turning it all the way around and getting dizzy at the same time. So we have no idea about its XY orientation, only the Z. We're only allowed one. Quantum mechanics will not give us any more. So for the L-equivalent one, we have it now. Energy depends on J only. So that means I have 3 quantum states that have the same energy. So we have a degeneracy. So for the J values, a degeneracy, we will need this later, is equal to 2 times J plus 1. So if J is 1, 2 times 1 plus 1 is 3, there's our 3 quantum states. Now, they are degenerate, they have the same energy. Why? Because there's no asymmetry. That was the whole point of that, one little simple little problem on the homework set, which is finding the degeneracies of these lower states. You found out when you had a particle in the box, and you changed the dimensions of the box, the degeneracy began to lift. So now I have a molecule that has 3 orientations, which really doesn't make a great deal of sense if you think about it, because the molecule is just tumbling through space. So how does the fact that it has only 3 different angles matter at all? It does if I took, let's say, the molecule was nitric oxide or carbon monoxide, which is a diatomic polar molecule. If I take a molecule with a dipole moment, I put the molecule in a magnetic field. Now I have an asymmetric force, and we will see those different being splits. And you're going to see that in the spectroscopy.
Because they're working in spherical space, our thetas are still from 0 to pi, correct? So
Theta, that's correct. Theta goes from 0 to pi, correct. And of course, then the XY goes all the way 360 degrees here. That's correct. We're going to need that again in a moment. So if I do this, go from j equal 1 and make this j equal 2, well, now we have m values of going from -2, -1, 0, 1, and 2. And so now the angles become more plentiful. So now you have 35.26, 65, there's your 90 degree, 114, and 144. So as the j gets larger and larger and larger, the amount of degeneracy and the number of angles at which to rotate then begins to increase by that dimension, 2j plus 1. This is a subject of just the one homework problem I'm going to assign today. It is problem number 3. Again, this is an intro P-Chem homework problem, so you got to deal with it. So first off, I say consider a rigid rotor equilibrated at 300 Kelvin. It said at this temperature, we know that the average thermal energy is about kT. Remember that, when I say average thermal energy, it's always kT, where K is now an exact number, by the way. Now consider the two such systems, okay? I have two 1 gram masses on a massless rigid rod of 1 centimeter length, okay? And then the second one is a hydrogen molecule, so you'll need to reduce mass for a hydrogen molecule, with an equilibrium bond distance of 0.7416 angstroms. Clearly, the first system is classical. The second system is quantum mechanical. So I ask first, what are the rotational energies of each system in the j equal 1 quantum state? The energy for a rotating quantum system is j times j plus 1 h bar squared over 2I, where I is mu times r e squared. Okay? So they're going to do that for both systems. In one case, it's a hydrogen molecule, the mu would be much tinier, in kilograms, not grams, by the way. And the equilibrium bond distance, of course, is small, and then you're going to have two 1 gram masses on a 1 centimeter rod. That'll make the eye significantly larger, and you'll see what happens to the energies. Okay? That's how this whole thing starts out. Now let's see, what are the magnitudes of the angular momentum for each system in the j equal 1 quantum state? Well, the angular momentum is then j plus 1 h bar squared. Okay? But notice there's no I in that. So should you get the same answer? In C, for each of these systems, estimate the quantum number the average system will be in if it possesses the average thermal energy. I'm going to do this later in just a moment, but the way to do that is you're going to take this energy of this system and set this equal to kT. Again, we will do it before we're done today. So you set the energy equal to the average thermal energy, solve for J. Now, in one of these, and you're not, don't try to solve for J exactly, okay? J is going to be a quantum number, so find it, so if it comes out to like 4.1, call it 4, okay? So don't try to do, so if you have fuel now, I'll show you that later. So find out, and now when you do this for the 1 gram masses, you might have a problem, getting a number. Right? Because the number of quantum states for two 1 gram masses on 1 centimeter rod is going to be gargantuan. The Bohr correspondence principle is coming into play. That's what we're doing. So for O's, then there's it. How many rotational angles does each system make with the z-axis? Well, the number of rotational angles is that number right there. Okay? So J is 1, you have 3 angles. This is what we found out. J is 2, you have 5 angles. Well, when you do your J for your 1 centimeter rod and 1 gram masses, your J is going to be gargantuan, meaning that there's almost an infinite number of angles, continuous. So the quantum system, when brought up to higher levels, matches than what we would expect to see classically. And then I say that compute the energy spacing from the first quantum state, the quantum state that you find when you do this problem here, you find a J, the next energy level is J plus 1. So calculate the energy of J, calculate the energy of J plus 1. Is it measurable? Is it a big energy? Is it a small energy? Turn it into a wavelength. Is it a wavelength that I could see in a spectrophotometer? Or is it going to be 10 to the minus 90th? Okay? So it is demonstrating, once again, as quantum systems come up higher and higher and higher, they begin to match with the classical. So it's a very straightforward and fairly simple problem. All right, so that tells us our orientations. What about the spatial? Now here's what I want to do. I want to generate the j equal to n equal plus 1 quantum state. Okay? So I'm going to go to, you might make a note that this is page 8, and I want to use this. So I want to generate a wave function. Now, because what I said, what I was getting here, this was how it was rotating. But what about the molecule? Is the molecule faced that way, or is it faced in a different way? So we want to find that out. So let's generate the wave function 2, 1. Well, first off, the n, j, m, okay, this is j equal to n equal 1. Well, the normalization constant is if j is 2, so that's 2 times 2 plus 1 or 5. We have 5 over 4 pi. Then I have 2 minus 1 factorial, which is 1 factorial over 1. Then I have a 2 plus 1, try to factor for 3, so that becomes like 1/6. 1, 2 times 3. And all these to the 1/2 power. So it comes out then with 5 over 24 pi 1/2. So there is then the normalization constant. Now I go to the next part, and I want the P 2, 1 Legendre polynomial. So for most part, all the polynomials you'll need will be contained here. You can always look them up. It's on page 7, so I need the P21. Well, that's this one right here. So I look at this and I say, okay, P21 of x is, that's what, let's see, 3x times the square root of 1 minus x squared. Now again, that's the polynomial. For us, x is cosine theta. So P21 of cosine theta is 3 cosine theta. Wherever I see an x, I replace it with the cosine of theta. Then this becomes a square root of 1 minus cosine squared of theta. Well, 1 minus cosine squared of theta, trigonometric relationships, is just the sine of theta. So this then ends up being 3 times the cosine theta times the sine of theta. So that is then the angular part. Now I just need to go to the last part, go back to page 8 here. I'm sorry, down below. So I've got this now. That's this formula right here. This I just got. Now I need e to the I m phi. Well, I'm wanting the L equal to, or j equal to n equal 1, so it just becomes e to the I phi. So now I have my entire wave function. It's far easier than using generating functions. So my wave function now, as a function of theta and phi, is this n, let me go ahead and write that in, 5 over 24 pi to the 1/2. I have 3 cosine theta, I have sine theta, and then e to the I phi. That's the wave function. Good. Okay. Now what I can do, I have this 3 here. I can bring it into here. And so this can be brought in, it'll be 9 times 5 is 45 over 24 pi to the 1/2. And then I have my cosine, theta, and the rest. Well, 45, 24, if I divide that by 3, it comes like 15/8 or something like that. So I can do 15/8 over 8 pi to the 1/2, and all. So I can collect the constants together if I want. You don't have to, but it comes into play. So that's what I've done here. So going down now, continuing, I said generate that. Well, there's the 5/24, and here's my 3 cosine theta sine theta I phi. I brought the 3 in, and there's my 15/8. So there's my wave function. Now, here's what I want to do. I want to know at what angle, spatial angle, is it more likely to be positioned. Okay, now we're talking about the tips. So this is the molecule itself. We did angular momentum before, okay, how it's rotating. Now I want to know about the actual position of the molecule. Okay? I'll tie them both together in just a minute. To do that, define the most probable position, and it's going to be a distribution just like anything else. To find the most probable position, I need to take the wave function absolute value squared. Okay? So the most probable position will be the absolute value squared, or psi star psi. Okay? That gives me a probability. This is going to be n squared. I won't bother to put in that number. Then I'm going to have a cosine squared theta sine squared theta, and really everybody's attention. We are in spherical space. To sample spherical space properly, we need a Jacobian, so I need another sine theta. Remember, spherical space at r squared sine theta. So whenever you do that, whenever you play in space, you gotta put that Jacobian in there. Now, this then becomes, I have an e to the minus I phi and e to the positive I phi. Complex conjugates. So this is going to go to 1, those together, so we don't have to worry about it. Now that's my probability. What I'm going to do is take the derivative, set it equal to 0 to find the most likely position. So I'm going to take this derivative, I'm going to pull the n squared out, I don't need it. I'm going to have the derivative with respect to theta of the cosine squared theta, now sine cubed of theta. Take that derivative, set it equal to 0, solve for theta.
What are these, and theta here is?
What's that?
What is this process for? What are we finding theta for?
We're trying to find, we know that there's going to be, this, I think that, for example, a p orbital. In p orbital, which is what these are, in p orbital, there's a higher probability in an orientation, and then as you go down, the probability to find the electron forms the shape of space. It could be d or p or s orbital or something like that. So I want you're going to have a shape of the space, and if we plotted that, we draw it. I'll be doing that later. But if I have the shape of the space, it's going to have a maximum probability going in some direction. I want to know what that is. So to find it, I simply took the derivative and set it equal to 0. Okay? Well, if I take that derivative, I've got I have cosine theta, and the derivative of sine cubed theta becomes 3 sine squared theta times a cosine theta, which gives me a square on that. Is that too fast?
Where did it make it? Cube? Cosine cube?
Oh, cube, thank you. Cube, thank you. Apparently it was too fast for me. All right, so that's first times the derivative of the second, and then the second times the derivative of the first is going to give me a negative. I have a 2 cosine theta. Then it becomes, that if it's negative, it was a sine theta, so it becomes sine to the 4th of theta. Again, setting that equal to 0. Well, I've got a cosine here, I have a cosine cubed there, so that becomes a square. I have a sine squared and a sine to the 4th, that becomes a square. So I get then that going ahead and taking this to, well, let me just do this. I have 3 cosine squared of theta that is equal to 2 times the sine squared of theta. If I bring that over to that other side. Dividing through by cosine theta, sine divided by cosine is a tangent. So I have 3 halves, is the tangent squared of theta, or the theta is the arc tangent of square root of 3 over 2. So I took the square root, and then took the arc tangent. So that's going to be my angle. So let's take a look at that. When I put that in place, there we are, I did it right. So the spatial distribution is, the square root of 3 has arc tangent, that comes out to be 50.768 and negative 50.7868 degrees. So now, as opposed to rotation, I orient the molecule vertically, and I bring the molecule down 50 degrees, which is going to be right around there. Now, so that is a spatial, it's going to go all the way around as well. You have a angular momentum orientation of 65.9 degrees, just like we did earlier. So that means it's spatially here, but the 65-degree angle is more here. So that means the molecule is wobbling. So it's doing something like, rather than spinning flat, it's kind of spinning in a, need to get a shorter meter stick. Do they come? We call meter sticks, don't they? All right, so there's a kind of a wobble there.
What did you say from this, that we can see the wobble in?
The space is 50 degrees. When I put the L equal 2, N equal 1 into the L0L, I get 65, almost 66 degrees. So there's my space. I take now my rotation goes 65 degrees, so it's at a little bit of a cockeyed angle, which means that the molecule, when I get it poorly, it's not rotating this way, it's kind of rotating in a kind of a wobbly type of fashion. It's coming into play. So again, that's the most probable. The angles, rotational angles are exact, but the position is the most probable. That's all there is to on that.
Also, why isn't the wave function, why isn't it a function of R? Like, we only care about theta and phi.
The R is related to how far the particles are from each other. And if R gets smaller and larger, we call that vibration. And so that's exactly where we're going next. So we finish the polyatomics. We'll do vibration next, and that'll be our third one. So then we'll have X, Y, Z, we have NX, NY, NZ, 3 quantum numbers for translation. Here's 2 more for rotation, and 1 more for vibration. There's all 6. 2 particles in 2 dimensions. 2 particles in 3 dimensions. All right, so we can get information. Now, here is just energetic numbers. This is nothing very difficult. I want to know how fast it's rotating. Well, there's the angular momentum. In rotational physics, the angular momentum is I times omega. So omega is the angular velocity. So I solve for omega. I need h bar, I need mu, and I need the equilibrium bond distance squared. Well, here's for hydrogen. And for chloride, hydrogen is 1 grams per mole, 35, and I divide by Avogadro's number. So the reduced mass is the mass of one times the mass of the other with a sum. And again, I put everything into absolute kilograms, so I do that as well. And so when I put my values in place, I get a rotational angle for the J equal 1 of about 9 times 10 to the 11th. And for J equal 2, 1.567 times 10 to the 12th. Now, if we have this 10 to the 11th and 10 to the 12th, the difference between those values divided by the speed of light is 22 wave numbers. That is in the rotational or microwave spectrum. So if I want to see what this looks like, or if I want to separate those out into different energies, I need to go to a microwave. And microwave does that very thing. So that kind of gives us a scale of what's that coming into place. And test this to see what happens. So here are the values for chlorine gas. Now, chlorine gas has a much heavier than the hydrogen. If I bring down in here, look what happens to the microwave spectrum. These values here, they get smaller and the spacing gets smaller. So if that chlorine went to 2 1-gram masses, you see what's happening? So this is the energy spacings essentially. As the masses get heavier and heavier and heavier and heavier and heavier, that drops to 0 and finally unmeasurable. And that's what problem number 3 has you look at. So put those back. Finally, before we turn to polyatomic molecules, we need to do a little bit of work on that. So for here, I do the same thing I'm asking you to do in the homework. So I say, all right, for the J goal 1, I don't care where to pick. No, I said for an energy value of KT, just like your homework, I picked 300 Kelvin. There's Boltzmann's constant. Now an exact number, I moved that and put it in place. So the average thermal energy in this room is about 4 times 10 to the minus 21st joules. That's about right. So taking this, solving for J times J plus 1, I just brought these terms all the way over, so there's a 2 mu RE squared KT over H bar squared. Produce that number, I get something on the order of about 20. So 4 times 4 plus 1 is 4 times 5 is 20. So it tells us that molecules are rotating. Now this is again for HCl. For HCl, the molecules are rotating on average at about the J before quantum state. So as opposed to the translation, which is way up there, the rotation, at least for HCl, is fairly low. See if I reproduce this, see if I can do this for chlorine. So bring that chlorine down. And now, let's see what I get. I didn't, now the J times J plus 1 becomes 3, I didn't write that down, so what's the square root of 351, which is approximately right. So that's about, the quantum number is about 18 or 19. So as we went from HCl, very light and modestly heavy, to Cl, heavier and heavier, the average quantum number went up. So for things like hydrogen fluoride or something like that, we're going to be a fairly low quantum state. But if I had something heavy like benzene maybe, or carbon dioxide, the average quantum states are going to get higher. So that's going to put us in a very interesting position later, is to figure out how do I treat this? Do I treat this as individual quantum levels, or can I do what I did with translation and treat things continuously? We'll evaluate that at that time, okay? So that kind of tells us what we find out of this whole system. Of course, when we turn this into the atom, hydrogen atom, it'll get a little bit more interesting. We'll be able to do more things with it because it'll be electrons that are in their transitions. But now we can find out that when we have a lot of degeneracy going on, that'll be important. I can lift the degeneracy by putting it in asymmetrical, magnetic fields or electrical fields or something along that lines. And of course, when you put it in an electromagnetic field, then that changes all that degeneracy, and that's how we get spectra. So that'll be the last thing we do in here before this comes out. But now we need to go just do a little bit of now almost classical work in finding center of masses, moments of inertia, and say, all right, how is that connected quantumly, quantum mechanically? After we get information, compute that. So I will save that for Friday, and then we'll finish up. And then I think I put the vibrational notes